Okay, so for our next example, we are going to do SF5 minus. So for this structure, if we generate the Lewis structure, we need to determine the total number of valence electrons in the structure. So for sulfur, we know that there is one of them, and it is in group 6. For the fluorine, there are 5 of them, and they are in group 7. And because this has a charge, we know we need to account for that in our tally, and since it's -1, we need to add an additional electron to account for the charge. So when we finish adding this up, we know that our structure should have 42 valence electrons. So we determine our skeletal structure, and again, our central atom is typically written first, so we have sulfur as our central atom surrounded by the 5 fluorines. And the next step, we give a single bond from our central to our terminal. So we draw single bonds from the sulfur to all of our fluorines. Then we give our fluorines an octet. We know that they are not an exception to the octet rule, so we give them each 8. So we have to draw 3 more lone pairs around each fluorine. Now once we've done that, we need to determine how many of the 42 valence electrons we have used, and we see that we've only drawn 40 of them, so we have 2 left over. And we know that if we have any left over, we put them on the central atom as a lone pair. So I've used all 42 of my valence electrons, and I've given everything an octet. If I look at the sulfur, I see that it's actually holding 12 valence electrons, but remember, because it is in period 3 and below, it's actually in period 3, we know that it can have an expanded octet. So this is the Lewis structure for this particular molecule, but remember, because there is a charge, we have to include our brackets and our charge. Now in terms of our 3D molecule, we look at the central atom and we see that there are 6 regions around the central atom. And that narrows it down a little bit in terms of what our shape is going to be. However, we have to look at what type of electron density is around the sulfur. So we see that we have 5 bonding pairs and we have 1 lone pair. So when we have this combination of electron density around the central atom, we know that it has a molecular shape of square pyramidal. Now, when generating the 3D molecule, we know we have a general structure where we have bonds where we have 2 in plane, then we have 2 going behind the plane, and 2 going in front of the plane. And again, this is in general for anything that has 6 regions around the central atom. So for this molecule, we would have 2 in plane, 2 behind, and 2 in front. So in the previous example, we had to pay special attention to where our lone pair was placed. In this particular example, because it's got 6 regions, when we only have 1 lone pair, it does not matter in which of these 6 positions you place the lone pair. So I will put the lone pair here and fill in my remaining terminal atoms. And the reason it does not matter where you put those lone pairs is because it doesn't affect any of the lone pair, lone pair, lone pair, bonding pair, and bonding pair interactions. So when you have 1 lone pair, you can put it in any of these 6 positions. Now, if we ask ourselves, what is the polarity of this molecule? You say that, yes, there are polar bonds. So we have polar sulfur fluorine bonds. So we know it can either be a polar molecule or a non-polar molecule. So we have to look, do we have a net dipole moment or do we not? Therefore, we have to look and we have to ask ourselves those questions. Do I have a lone pair bonded to the central atom? And because I do, I know that this molecule is automatically polar, meaning that there is indeed a net dipole moment. Now, if we go down and do an additional example, let's look at, let's do xenon tetrafluoride. We draw the Lewis structure for xenon tetrafluoride. We add up the total number of valence electrons. We have one xenon, it's in group 8, it's a noble gas. We have 4 fluorines, and we have 36 valence electrons. We know that xenon is the central atom, and we surround it by the fluorines. Then we give our fluorines an octet. So fluorines are not an exception to the octet rule, so we know that they want 8. Then we look, out of the 36 valence electrons, how many have I drawn? And you see that I've drawn 32, so I have 4 left over. And we know we place them on the central atom as lone pairs. So we see that we've used all 36 of our dots. The fluorines have an octet, and when we look at the xenon, we see that it's actually holding 12 valence electrons. Now, this is acceptable because remember, xenon is period 3 and below, so it has an expanded octet. So this is the Lewis structure for xenon tetrafluoride. Now, in terms of a 3D model, what we see is that we have 6 regions around the central atom. So again, it narrows it down a little, but we have to consider what type is present. So we have 4 bonding pairs, and we have 2 lone pairs. Now, when we draw the general structure, again, remember we're going to have our central atom, 2 in plane, 2 behind, and 2 in front. Now, with this combination, we know that we're going to have a molecule shape of square planar. So, we draw our xenon, we have our bonds in plane, we have our bonds going behind and coming in front. Now, in the previous example, it did not matter where we put our lone pair. We could put it in any of those 6 bond positions. But for this particular structure, when we have more than one lone pair, so in this case we have 2 lone pairs, we have to put them opposite each other. So any lone pairs, if you have more than one, they have to be opposite each other. And the reason for this is due to decreasing those lone pair interactions. We want them as far away from each other as they can get. So if I put one lone pair here, I have to put my other lone pair exactly opposite it. And then I stick in my fluorines. And we have now correctly generated the 3D molecule of this structure. So remember, when you have 6 regions of electron density, one lone pair can be placed in any of those 6 bonds. However, if you have more than one, if you have 2, they must be opposite each other in order to decrease lone pair interactions. If we look at the polarity of this molecule, we see that it has polar bonds. Therefore, it can be a polar molecule or non-polar molecule. So then we ask, does it have a net dipole moment? And since there are lone pairs on the central atom, we know that this is a polar molecule.